How do spacecraft perform orbital maneuvers? Have you ever wondered how spacecraft change their paths in the vastness of space? The answer lies in a fascinating process called orbital maneuvers. These maneuvers allow spacecraft to adjust their velocity and trajectory, enabling them to orbit celestial bodies effectively. At the heart of these maneuvers is a concept known as delta V, which refers to the change in velocity required to modify an orbit. Understanding delta V is essential because it determines how much fuel a spacecraft needs and what types of maneuvers are feasible. Spacecraft utilize onboard propulsion systems, such as thrusters, to generate the necessary delta V by firing in specific directions for set durations. One common type of maneuver is the Hohmann transfer. This method is fuel-efficient for moving between two circular orbits. It involves two engine burns. The first burn shifts the spacecraft into an elliptical transfer orbit, while the second burn circularizes the orbit at the new altitude. Although this method conserves fuel, it does take longer than some alternatives. Another maneuver is the bi-elliptic transfer, which is ideal for significant changes in orbit altitude. This technique involves two elliptical orbits and 3 engine burns. It can be more fuel-efficient than a Hohmann transfer when the altitude change is substantial. Spacecraft also perform plane change maneuvers to adjust the inclination of their orbital plane. Since changing direction requires changes in velocity, these maneuvers are most efficient when executed at points in the orbit where the spacecraft's velocity is lowest, such as at the apogee of an elliptical orbit. Gravity assists, or slingshots, are another clever technique. This method uses the gravitational field of a planet or moon to change the spacecraft's speed and direction without consuming additional fuel. It is particularly useful for missions venturing beyond Earth's orbit. In addition to these larger maneuvers, spacecraft perform smaller adjustments like orbit insertion, which allows them to enter orbit around a celestial body. They also circularize orbits to make them more circular, maintain their position in orbit through station keeping, and execute rendezvous maneuvers to approach other spacecraft or objects. Planning and executing these maneuvers involves trajectory optimization. Mission planners calculate the timing, direction, and magnitude of engine burns to achieve mission goals while minimizing fuel consumption. Each thruster firing is carefully simulated and tested to ensure accuracy. Spacecraft carry propellant and propulsion systems designed to provide the necessary thrust for these maneuvers. The efficiency of these systems is measured by specific impulse, which indicates how effectively a rocket engine utilizes propellant. In summary, orbital maneuvers transform raw rocket power into controlled movement. This capability allows satellites to reach and maintain desired orbits, conduct scientific observations, and support exploration missions beyond Earth. Understanding these maneuvers is fundamental to all satellite systems and space missions.